Hey, welcome to my first devlog for RundownRover. This is an engineering game where you try to manage power and divert power from different components to reach your destination. This game was initially developed in a game jam, and there was a lot left undone that I'm hoping to complete. One important aspect of this game involves terrain information that's in a render texture. I use that to supply a VFX graph with information, but I also want to change the incline of the rover as you're driving. When I was reading up on how to obtain texture data from the GPU, every source I was reading kept on mentioning ReadPixels from a Texture 2D, but also stating that this was not performant and not the preferred method, and instead pointing to AsyncGPUReadback calls, which the documentation for on Unity's site is pretty sparse. So if you're here, there's a good chance you ran into some of the same issues I did. So before we begin, I'll give a quick summary of the outcomes. So AsyncGPUReadback will only accept persistent allocation for your native array. Native array has to be persistent. You can't use temp or temp job. It will throw an error. AsyncGPU is definitely the way to go if you can afford to not get updates every frame. This becomes more apparent the larger the texture you're reading from is, and that's regardless of the number of pixels you're actually reading from that texture. I found no way to persist the native array between calls when using AsyncGPU within a coroutine. Fortunately, this doesn't actually have to be done in a coroutine. You can call AsyncGPUReadback functions within your normal update loop. You'll just have to track the result state yourself or use a callback function. So if you want to stick around, let's go ahead and set up a material with a scrolling noise texture. I'll be doing this a bit quickly. We're going to use this vehicle to incline, and here I'm creating an empty game object to contain all the objects I need for the render texture and the terrain. I'll put all of this in that parent object with a new layer terrain texture and set all of these objects to that layer and set the camera to only read that layer so we don't get any other information in the texture. And for the terrain texture, I'm going to use a basic unlit shader graph with a couple octaves of noise, which we can scroll. The goal is to scroll this texture as we move and update the incline as if this were a height map. Now we can make a basic script to handle the faked movement of our vehicle. Note that I have this movement set up in just 2 dimensions. We won't bother changing our vehicle's heading. We'll just move omnidirectionally forward, backward, left, and right. We'll need to reference the material for the terrain in order to update its parameters. And after adding this script to the player car, we can assign the material we'll be manipulating. So the first method is pretty straightforward. We're going to need to reference the render texture, and we'll make a new texture 2D to store this information in. For the size of this texture 2D, let's define a square width that will pull from the render texture. And for the ReadPixels method, we need to use that square width to define a rectangle. This will all be called from the update loop, and we'll return the pixels into our texture 2D for use. For calculating the normals, we'll use 3 points. Since we have 4 points making up essentially a quad that we've pulled, we can do the calculation twice by creating 2 triangles from the points we have and averaging the normals. Now that we have our target normal, we need to rotate our object's normal while keeping the heading in the correct direction. To do this, we can define our from look based on the current normal and the to look based on our target normal, keeping both of these having the same forward direction. In this case, since we're not rotating the vehicle at all, we can use the vector3.forward. Then we lerp our current rotation to the desired one. And you'll note here, this model has a rotation by default when I exported it from Blender. So we'll just stick this thing inside of an empty game object and adjust its rotation locally there. And move the script up to the parent game object in my case. You shouldn't have to do any of this. And there is an issue with the order of the points that I'm using for the normals. We can also move the normal checks outside of the logic to check the texture, since these are unrelated. Now that the car is moving, it's a little too subtle, so we can add a variable to increase the intensity of that calculated normal. And we now are reading texture data from the render texture and using it to calculate an incline. Let's try out the AsyncGPUReadback function in an iterator. First, we need to pass in a native array of bytes to hold the data. We can use persistent allocation for now. So to the RequestIntoNativeArray function, first we'll pass in the native array by reference, then the texture data we want to read from. We aren't using any MIP levels, so index 0 is sufficient for that. And then the X and Y are paired with the width and heights to determine the same thing we did with ReadPixels, the rectangle that we want to read from. And finally, since this texture data is 2D, we can use Z equals 0 and depth equals 1. For now, we can put all of this into 3 channels. Note that's why I multiplied the size of the byte array by 3. And within this iterator, we'll check if the request is done. If it's not done, we can return and check again next time. When it is done, though, we will take the byte array out and populate our points based on the corners of the rectangle we wish to get. Note I'm starting from the top left and going counterclockwise, and the vectors I'm creating here have the values from the texture in the Y slot. And I'm manually populating the X and Z values for the vector 3 points based on where on the square they should reside. Here I'm making a small correction to the calculation for the ReadPixels function. And don't forget to dispose the native array when you're done with it. Let's go ahead and log out the values of the byte array just to see what these look like. And to actually run this iterator, let's start the coroutine from the update method. Note we're currently getting a 2x2 rectangle of pixels back, but since this is RGB, we have 3 bytes for each pixel in our array, resulting in 12 bytes in this array. Now that we have both methods implemented, let's prepare to make comparisons. First, I want to be able to toggle between the 2 methods using the spacebar. And next, I would like to see how frequently these are each getting called. I would like to note here that I did make an error previously, and I am calling AsyncGPUReadback too many times at this point. I'm calling it every frame, and it's returning the correct number of results, but a lot of them are returning at the same time. We'll fix this later. We'll also set the default movement to vector 2 up, so we're constantly going forward. And to open the profiling window, you go to select window at the top, then analysis, then profiler, and ensure the red dot is selected to record the profiling information. And now we can see the profiling information is populated as we enter play mode. Note the logs we're sending to the console. It looks like we're making about 163 read pixel calls per second, and when we switch to the AsyncGPUReadback approach, we're getting roughly the same number. Before we move on, I'd like to show you what happens with a larger render texture. So our render texture defaulted to the size of 256 by 256. Let's go ahead and increase it to 4K. Here I'm making one slight adjustment to the calculation for the pixels we read from on the render texture. And I would also like to be able to change the width of the square we scan from the texture that we pull. We'll track the old value, and anytime the current value doesn't match the old value, we'll go ahead and recreate that texture 2D with the correct size. Now with the 4K texture, we see that the texture 2D method has us down to about 64 frames per second, while the AsyncGPUReadback function is able to get us 80 calls in a second. And we're still only reading in 4 pixels from the texture in each of these cases. Back to the script, I'd like to clear out the stats about each method anytime I change the scan width as well. And now I've opened up the stats window where you can see the actual FPS, not just the calls per second that I'm logging below. And we're currently using the async call. When I switch back to the texture 2D method, you'll see the FPS drops about 15. You can see that change in the profiling window as well. Let's go ahead and try to read in 1000 by 1000 pixels. First with the async GPU, and then with texture 2D. Not great in either scenario, but let's revisit this shortly. Looking at one of the spikes for the async method, we see a large amount of time spent on garbage collection in the hierarchy view. So looking further into the AsyncGPU method, especially with the use of native arrays, it makes sense that you might want to use temp or temp job for the of your native array, since we're only letting this array live long enough to return the results. However, if you try this, it will throw an error informing you that AsyncGPUReadback cannot use temp memory. So in every case with AsyncGPUReadback has to be persistent, which is fine. How about if we're using persistent memory, how about we use it repeatedly? And what I've found is you'll get an error stating that the native array can no longer be accessed and has been invalidated. But this happens just because we're passing this to a coroutine. If you don't pass it to a coroutine, you don't have this error. Since AsyncGPUReadback is already an async function, we don't really need to put it in an iterator. I can just manually check if the request is done myself. Before we try that, let's just go ahead and check the default properties for a request. Okay, so by default, we see that a request should have its done property equal to true and has error also equal to true. We can use this. We would expect a valid request to be done and not have an error. So let's copy our iterator, rewrite it to function within the update loop. Now we saw that the request will default to done, so let's also ensure that has error is set to false before trying to get the result. And we can try it out. It looks to have similar performance to the coroutine, but we're seeing fewer calls per second. This is due to me actually calling this only when it's returned. We can kick out the size of the array we're sampling. And I see large garbage collection calls, still in line with the coroutine, but we will be fixing this shortly. To correctly see how many calls we're returning per frame, I went ahead and added another debug stat to only increment once when any async call returns in a frame, so we can see how many times I was wasting calls to this API. So it's not very noticeable at 4 pixels, but I was wasting quite a few calls by starting another coroutine when previous ones hadn't completed. So one other small improvement, since I'm only interested in height data, I could just read in the texture in R8 format rather than RGB24. That would give us only 1 byte per pixel, and we'd get 1 channel back. So with all of this in place, I wanted to compare the performance of using the async call in a coroutine versus within the update loop. And in both cases, we see again garbage collection was problematic, and I had a terrible time solving this issue. So I knew that having to declare the native array in the same context as the iterator was going to be a limitation using the coroutine, since I had to use persistent allocation with any AsyncGPUReadback operation. So I tried focusing my efforts on the non-iterator method, calling it directly within the update loop. I tried several things, pinning the native array to the GC handler, using the unsafe utility, pointing the address of an array, but I had a ton of trouble finding out why I was getting so much garbage collection. So it turns out I was copying the entire native array into a byte array before using the values for it. This wasn't a huge issue when I was using small arrays, but when using larger ones, this was creating copies way too frequently and those were having to be collected. So simply pulling out the few values I needed directly from the native array fixed my garbage collection spikes. Now that you've made it through all that, here's the final performance comparison of Texture2D ReadPixels versus an AsyncGPUReadback request into native array to get texture data to the CPU. With a small render texture and a small number of pixels read, you'll just incur a small cost using the ReadPixels function. But as you increase texture size and the number of pixels that you're reading, the gap between the two methods will increase drastically. To the point that at a 4K texture size, which, by the way, I wouldn't recommend, just writing to the 4K texture is costing me quite a few frames. But using the 4K texture and reading in just 20 by 20 pixels, ReadPixels is dropping me an additional 20 FPS over the AsyncGPU method. So to recap, AsyncGPUReadbacks can save you in terms of FPS as long as you're comfortable with the updates being less frequent, and this gap is much more noticeable when you're reading from a large texture. Thanks for joining, and you might see me again if I have anything else that I think is interesting or useful. And I've included a link to the gist containing this example script, so you can just copy that if you need to implement for yourself. Anyway, take care.